gonna start right now. Yeah. All right. So the reduction formulas, okay? There's really one place that you're gonna see these again, and that is in Calc 2, okay? So for some of you, that could be as early as this summer, if you're like really going for it, okay? And so with the reduction formulas, okay, they actually come from the double angle formulas that we learned at the beginning of class. So if we take cosine of 2 theta, and we knew that one of the variations it's equal to is 1 minus 2 sine squared theta, okay? And we want to solve for sine squared. Well, if I want to solve for sine squared, I could add it to both sides. And maybe at the same time, I'll subtract that cosine 2 theta to the other side. Okay. And then I'm going to go ahead and divide it by 2 so I can get the sine squared by itself. Okay. Now it turns out that if you take the square root of what we have right here, you're going to get the half angle formula for sine. Okay, so that's where that formula comes from. That's why there's a square root, because we took the sine squared one and we just wanted sine, not sine squared. Okay, but this is the power reducing formula for sine. Okay, we have one for cosine, we have it for tangent, but probably sine and cosine are the most common ones that you're going to see again in Calc 2. So if we take one of the other cosine double angle formulas, 2 cosine squared theta minus 1. And we do the same thing where we're like, let's find cosine squared. We can add the 1 to both sides. And we can divide by 2. And this will give us the reduction formula for cosine squared. Okay. Now again, these two are probably the most used in Calc 2. But I'll show you the tangent one just so that you have it. If you have the tangent one, all you do is you take the sine and you divide by the cosine. So the power reducing formula for tangent squared theta is sine squared divided by cosine squared, which when we simplify what we have ends up being 1 minus cosine 2 theta over 1 plus cosine 2 theta. Okay. So these are the 3 reduction formulas, okay? And now with these reduction formulas, why are they really important? Well, let's take a look at an example that's actually going to include stuff we're going to learn after we come back from Thanksgiving break and kind of help you put into perspective why that's going to be important as well, okay? So kind of a long problem, so let's do it on the next page. So you might get a question that looks like this. Find the area enclosed by r equals 2 plus 2 cosine theta. Okay. So when we come back from Thanksgiving break, we're going to learn how to graph r equals 2 plus 2 cosine theta. Okay, so that's one thing that you will know by the time you finish Math 104. Now, in the meantime, if we throw this on Desmos, then yeah, the graphing never goes away. Yeah, so we're gonna go ahead and pretend like we use Desmos to graph this, okay? But if you choose to do the art project, which is like the last 2 math and writing assignments, you could exchange 2 assignments for 1 sort of art project, you'll get a chance to play around with these graphs and see like the really cool pictures that they make. But this graph in particular looks something like this. So it kind of looks like a sideways heart. Okay. Now, when we're looking at this, a couple important points on here. Okay, this happens to cross at 4. This crosses at 2 and at -2. Okay. And we're going to learn in Calc 1 at the very end that there's something about area that we can use calculus for. Okay. And so when we look at area, the area formula we're going to have is we're going to go from 0 to 2 pi of 1/2 r squared d theta. Okay. It's a cardioid, close, cardioid, not a carotid. All right, so we have this formula, and let's just plug in what we have. So we have the integral from 0 to 2 pi of 1/2. Now instead of r, I'm going to go ahead and put in 2 plus 2 cosine theta. So 2 plus 2 cosine theta. And it's r squared, so I need to square it. Okay. It's okay. You don't need to know what an integral is yet. But I will tell you that integrals are how we find area. Okay. It's the area under a graph. Sometimes it's the area between graphs. We can also use integrals to find volume and things. So lots of applications for it. Okay. Also, if you're looking maybe more directly at computer science, like when you're looking at sums of things, like adding a whole bunch of things together that follow a certain pattern, we actually use integrals for that as well. Okay, but at this point, what we can do is use what we know about arithmetic and kind of FOIL out from here, okay? So we're gonna leave this 0 to 2 pi, we're gonna leave the 1/2, and when I FOIL out this part, I'm gonna get 4 plus 8 cosine theta plus 4 cosine squared theta d theta. Yes, we could say the integral part of computer science. Okay. So now I'm going to do a little bit more algebra. I'm going to distribute that 1/2, and we should get the integral from 0 to 2 pi of 2 plus 4 cosine theta plus 2 cosine squared theta. Okay. Now, this next part is optional, but I find that a lot of times the smaller we keep our numbers, the easier the computations are going to be later. So when I look at this question, I notice that there's a greatest common factor of 2. So I'm going to pull a 2 all the way out to the front. Okay. So this is what we've done so far. So we said, hey, here's this graph. Let's see what it looks like. It is indeed called a cardioid. And then we said, hey, there's this formula or this application of calculus where we can find the area using integrals, and this is what our formula looks like. And then we just plugged in some things. And so everything else that we've done after that has been algebra, okay? So now we're gonna do a little bit more algebra before we do the calculus again, okay? And that is this part. Cosine squared theta, okay? So is our r always from the equation? So they will usually give you the equation right? So at the very beginning, they said r equals something. So we use that same r in the equation. Yeah. Once in a while, they'll give you an equation that's like r squared equals something. If you want r, then you just take the square root of that something. Yes, yes, exactly. Cardioid, cardio, it's like a heart. Okay. So it turns out when you get to calculus, all right, so by about April, we'll know how to do this part, finding the integral of 1. We'll be okay with that. By about April, we'll also be okay finding the integral of 2 cosine theta. But what we're not going to know how to do until Calc 2 is this part, the integral of cosine squared, okay? And so what we're going to do to make it into something that we can integrate is we're going to make a substitution using the reduction formula. So if we look back at our reduction formula, cosine squared theta was equal to 1 plus cosine 2 theta over 2. Okay. And sometimes we write it as 1/2 plus 1/2 cosine 2 theta. Like sometimes we split it into 2 fractions. That's sort of a personal choice. I'm going to use the split fractions to substitute in. Okay, but as you get to like April or May of next year, I think you'll have a better idea of which one you prefer. So all I'm going to do in this next step, I'm going to keep the 2 in the front, integral from 0 to 2 pi, 1 plus 2 cosine theta plus, but instead of writing cosine squared, I'm going to write 1/2 plus 1/2 cosine 2 theta. So all I've done right now is substitute. Instead of cosine squared, I wrote that formula. Okay. What is d theta? So the d theta goes with the integral symbol in the front. So together they're sort of like the sandwich, like everything in between there is what we're going to integrate. That's a short answer. Okay. We'll talk about it probably March or April, like what the d theta stands for. Okay. All right. No, not in this context. It's not a derivative. Yeah. Okay. These are good questions, folks. So before we integrate, before we do the calculus, let's do one more thing, which is combine any like terms that we have in the whole thing. So I notice that there is a 1 and a 1/2. So 1 plus 1/2 is 3/2. Then I still have my 2 cosine theta, and I still have my 1/2 cosine 2 theta. So the only things I could combine were the 1 and the 1/2. I cannot combine the theta and the 2 theta because theta is one angle and 2 theta is a different angle. Okay. All right. So now let's do the calculus piece. Okay. So maybe let's switch colors. So I'm going to keep the 2 out front. But when we take an integral, we can do the integral of each term by itself. So the 3/2 we can do by itself. then the 2 cosine x, 2 cosine theta, and then the 1/2 cosine 2 theta. Okay. So the integral of 3/2 is going to be 3/2 theta. And that's something you folks will know by like late March, early April next year. Plus the integral of 2 cosine theta is going to be 2 sine theta. Plus the integral of 1/2 cosine 2 theta is actually 1/4 cosine 2 theta. They might be. And then at the end, we're going to draw a line, a vertical line. We're going to write 2 pi at the top of that and 0 at the bottom. Now, all this means is we're going to plug in 2 pi first into our whole long equation, and then we're going to plug in 0 into our whole long equation. And we're going to subtract those two. Okay. Now, since I have this 2 hanging out in front, I'm going to go ahead and distribute that back in before I plug in my numbers. So I'll get 3 theta plus 4 sine theta plus 1/2 cosine 2 theta. Plugging in 2 pi, plugging in 0. Okay, so you plug in the top number first. So here we go. 3 times 2 pi plus 4 sine 2 pi plus 1/2. Whoa, sorry, this was not cosine, it should be sine. 1/2 sine of 2 times 2 pi. So after we integrate, there's no more integral symbol. That means there's no more d theta. Okay. And then we're going to plug in 0 into that same long equation. Okay. And even though you learned the unit circle way back at the beginning of Math 104, it comes back again because we got to know all our values in order to simplify. Okay. So let's see. This part you folks can help me with. When I take 3 times 2 pi, what do we get? 3 times 2 pi, what do we get? 6 pi, good. Okay. Tell me what sine of 2 pi is. What's that? 0. So guess what happens to this? It goes to 0. Okay. What about sine of 4 pi? Well, that's not on our unit circle, but that's why we have to know how to count extra times, right? What do we get for sine of 4 pi? Also 0, very nice. Okay. So already I have 6 pi plus 0 plus 0. So a lot of things are dropping out. That's okay. Minus. What happens to 3 times 0? Now that goes to 0. This goes to 0. This goes to 0. So we have like minus a whole bunch of zeros. And our answer is 6 pi. Okay, but just to kind of circle back to our original diagram, okay? What that means is this beautiful little cardioid here, if I wanted to know how much space is inside the whole cardioid, it's exactly 6 pi. Okay, so all this work we did, yeah, but it's really nice to count by. All right, so all of this work we did was just to say how much area is inside of it. It's not really 3 circles because the 2 pi, when we talk about a unit circle, is the angles inside of it. I'm not asking about the angles, I'm actually asking about the area. Okay. So if we think about the unit circle, I think what you are maybe sort of confusing a little bit is when we have a unit circle, we know that's a circle with a radius of 1. What we're saying is like, what's the area inside there? So like pi r squared, the area inside this is pi. So it's not really 3 circles with a radius 1, it's actually like 6 circles with a radius of 1 would fit inside of that cardioid. Yeah. Yeah, there are so many uses for it. Okay. But this is literally like the one time in your near immediate mathematical future that you'll see this reduction formula. And it's really just this one spot here where we underlined in the pink. So literally right here is the one place that you use the reduction formula for. Okay. Are there any other questions about this particular problem? Okay, let me